In exercise 2 on page 83, we're going to use the first isomorphism theorem to prove that two groups we are interested in are isomorphic. So this is how this theorem is used. So we have two groups here. We have Z mod the cyclic group generated by K, and we want to show that that group is isomorphic to Z of K for any integer K greater or equal to 1. So how do we use the first isomorphism theorem on this? Well, we need to find a homomorphism. And if we can find a homomorphism that has as its kernel this cyclic group generated by K, and if for that homomorphism ZK is the image, then we get the result for free, because that's exactly how this theorem works. So we need to find a homomorphism that has a certain kernel, and then we have to show that the group on the right hand side, ZK, is the image of that homomorphism. So, strategy. Find a homomorphism. Find a homomorphism phi from our main group Z to ZK that is onto and whose kernel is the cyclic group generated by K. So this is how this is going to work. Okay, can you think of a homomorphism that would do the job? How are we going to define this homomorphism? So it goes from Z to ZK. Well, let's take an integer and let's map it to the integer mod K. So what is this doing? It's just going to take an integer and it's going to send it to the remainder after we divide by K. So what is the kernel of this map? Let's see if we can find the kernel of this map. Well, 0 is definitely in it. What else gets mapped to 0? So what else is 0 if we mod out by K? Well, the first thing that's 0 is K. And then the next thing is going to be 2K. And then the next thing is going to be 3K. And the next thing is going to be 4K, and so on. So it's all the multiples of K. That is our kernel. Okay. Now, we need to show that this map phi is a homomorphism. Okay, so how do you show that it's a homomorphism? So we have to show that phi is a homomorphism. We have to show that it's onto homomorphism. Okay, we have to show that it's onto and we have to show that the kernel is equal to what we want, the cyclic group generated by K. All right. Do we have a homomorphism? Well, let's look. So if we have two elements in Z, then is the operation preserved? What's phi of A plus B? That's equal to A plus B mod K that is equal to A mod k plus B mod k. The whole thing again, mod k. But that is exactly phi of A plus phi of B. And so, yep, our operation is preserved under the homomorphism. So it's a homomorphism. Okay, well, is it onto? Let's see. So let's take something in the image. Well, if it's in the image, so B, let B be in the K, then how big can B be? It can be 0, it can be 1, it can be 2, all the way up to, well, not K anymore. K minus 1 is the biggest that it can possibly be. Okay, so we have that 0 is less or equal to B and strictly less than K. And so can you find something that maps to B? Well, how about B? Phi of B is equal to B mod K, which is equal to B. So we found something that hits every element in ZK. So it's definitely onto. Then the last thing is to show that the kernel is what we want it to be. Okay, so how do we do that? Let's take something on the left-hand side, show that it's in the right-hand side, and vice versa. And we're going to do that with a bunch of equivalent statements. So we'll start with an element in the kernel. But when is something in the kernel? Well, it's in the kernel if and only if M mod K is equal to 0. But that is equivalent to saying that M has to be a multiple of K, so it's equal to P times K for some integer K. But that is equivalent to saying that M is an element in the cyclic group generated by K. Because remember, what is K? What is in that cyclic group? Our operation is addition. And so we have K, K plus K, K plus K plus K, K, and so on. So we have K added together however many times. So we've shown that the kernel is exactly equal to our cyclic group generated by K, what we wanted. So then we can put the pieces together. Since phi is onto homomorphism, so phi is an onto homomorphism. I can't spell. Homomorphism that has the right kernel. The kernel of phi is the group generated by K. So our isomorphism theorem tells us that Z mod K is isomorphic to ZK. And that's how you use the first isomorphism theorem. You have to find your homomorphism. You have to show that it's a homomorphism, that it's onto, and that it has the right kernel. And then you get that the factor group mod the kernel is isomorphic to your image.